Hello once again. This time around, we're going to take a look at logarithmic and exponential equations. So we've had a little bit of time. We've spent some time with exponential functions, and we've spent some time with logarithmic functions. Uh, at this point, we now know those are inverses of each other. Um, and we've also taken a look at how they model certain situations in the world around us, certain data sets. So modeling is only part of the story, though. If you're going to model something with a function, the purpose of that model would then be to learn more about the situation or make predictions about that situation. So you're going to need to be able to solve equations that come about from these models. Um, so let's say you've got a retirement account that is earning you on average 8% per year. Um, in interest and gains, and you know how much is in there now, and you want to know, hey, when will there be $500,000 in my account? Well, if you're going to answer such a question, you'd first have to model it with an exponential function, but then you're going to end up solving an equation. You're going to plug in 500,000 for the amount after time t, and then solve for t and see how long it's going to take before there's 500,000 in your retirement account. So um, we now need to take a close and specific look at how to solve equations that involve logarithmic and exponential functions. We're going to use a whole lot of the properties that we discussed in a previous section. So let's start with log equations that involve a log with a variable in its argument. So that's important. So a log equation, um, one variable will be in the argument of a log, or will be the base of a log. That's what we mean by a log equation. So for example, this is a log equation because the variable is in the argument of the log. If we had something like this, that's not a log equation. This is just an algebra 1 equation. Log base 2 of 8, that's just a constant. It's just a constant. So x would just be 6 minus log base 2 of 8. That'd be the answer. It's not a log equation. So that's not what we're solving. So we're interested in solving equations where the variable's either in the argument of a log or the base of a log. Okay, so let's take a look at this first one. We want to solve log base 2 of 1 minus 2x equals 3. Let's first do the domain. We need to know what values of x are even valid for this function. So let's do the domain real quick before we solve. So 1 minus 2x, it's the argument of a log, so it's got to be positive to be a real, so that log represents a real number. And then we see that x has to be less than 1/2. So as long as we get an answer that's some real number less than 1/2, then that's a valid solution to this equation in the real number system. Okay, so notice this is in log form. So notice the equation is in log form, meaning we have log base a of x equals y. It's just in log form. Now, why does that matter? How is that helpful to us? Because we know how to switch that to exponential form. So if I take log base 2 of 1 minus 2x equals 3, I can switch that to exponential form. So this is the base, that's the exponent, and that's what it equals. So it'd be 2 cubed equals 1 minus 2x. Well, 2 cubed, that's 2 times 2 is 4, times 2 is 8. So this would be 8. Subtract 1, so we're going to get 7. So we get negative 7/2, which is definitely smaller than 1/2. So that is a valid, that is in the domain of that function, therefore it's a valid solution to this equation. So notice we just switched from, we just went from log form to exponential form. So we just got our first method by which we can solve a log equation. Um, we could switch from log form to exponential form. So that's handy. All right. Let's try another one. Let's try another one. Notice that this one is already always, not always, sorry, is already in log form again. But notice that x is the base. So my domain, the base of a log needs to be positive. So x has to be positive. So as long as I get a positive value for x, it's a valid solution to this equation. So again, let's steal that method we just did. Let's go from log form to exponential form. So it'd go base to this power equals that. So logs are exponents, so 2 is the exponent. So it'd be x squared is 64. So x is negative 8 and 8. However, x is the base of a log and x has to be positive. So we really just get positive 8. X equals negative 8 is an extraneous solution, meaning it got picked up along the way along with the solution we wanted. So in our search for our solution, we got what we wanted, but we got this extra like hanger on, right? Like like a barnacle to a ship. It's like the ship gets where it wants to go, but then it's covered in barnacles. Ah, dang it. So 8 is what we wanted. Negative 8, we toss it aside. Okay, so another property that we're going to use quite a bit when solving log equations is we're going to make use of the fact that if log base a of m is equal to log base a of n, then the arguments must be equal. All the same restrictions apply. M and n have to be positive. A has to be positive. All the same restrictions we've always had for logs are in play here. So if two logs of the same base are equal, the only way they could be equal is if their arguments are equal. I mean, that's it. There's no other explanation. So, for example, if I've got log base 6 of 10 equals log base 6 of x, there's one and only one number that this could be. It's 10. That's it. It's the only option. Okay, so we're going to exploit that. By the way, if you're curious why it's called the one-to-one property, it just goes back to the graph of a log, right? So let's say you've got a log. Let's say this is y equals log base a of x. It's just simply saying that when you plug in an x value, there's only one possible output because log functions are one-to-one. For every x, there's only one output. So, and for every output, there's only one input, right? It's monogamous. It's a monogamous relationship. So if I have log base 6 of 10 equals log base 6 of what? Well, these are the same log functions. So it'd be this, it'd be a graph like this, except log base 6. And it's just simply saying that if the output is log base 6 of 10, there's only one input that gives you that output, and it's going to be x going to have to be 10. That's the only thing there is. So for every input, there's one and only one output, and for every output, there's one and only one input. That's why it's called the one-to-one property. All right. So how does that help us? Well, it turns out it's actually quite helpful. So for this log equation here, 2 times log base 5 of x equals log base 5 of 9, using my earlier property, I can move the 2 up to the argument. Oh, we should do domain first. See? I got in a hurry there. Let's do domain. X is the argument of a log, so x has to be positive. Okay, now we know our domain. So now let's take this 2 and move it up to the exponent on the argument. So this would be log base 5 of x squared equals log base 5 of 9. But notice the left side is a log base 5 and the right side is a log base 5. The only way that two logs that are both base 5 could be equal to each other is if their arguments are equal. So x has to either be -3 or 3. But remember, my domain is that x has to be positive. So my only answer is 3. -3 is extraneous, right? This one is extraneous. Let's try another one here. So I've got log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. Notice they're both log base 5, and I'm adding them together. And earlier, we saw that two logs with the same base being added together, you can combine those. Oh, once again, I forgot the domain. Man. So x plus 6 has to be positive. So x has to be bigger than -6. But x plus 2 has to also be positive. So x has to be bigger than -2. So the domain for this whole thing is, if this is the number line and this is -6, we're saying that everything bigger than -6 works, but the other one only allows -2 and bigger. So the domain for the whole thing is that x has to be bigger than -2. That's where they overlap. That's it. It's all that's allowed, or x value is bigger than -2. Okay. Now let's solve this thing. So I have two logs with the same base being added together. We know that from earlier, we can use one of our properties where I keep the base and I multiply those arguments. Yeah, I guess I won't skip that step. I got plenty of room. So I can multiply those arguments together. And then I get x squared plus 8x plus 12, I think, if I do that right. That's log form, so I'm going to switch it to exponential form. And I eventually get this quadratic that has the same solution set as the original equation. So let's solve this quadratic here. And I get -1 and -7. -1 and -7. But the only x value in the domain that solves this is -1. -7 is extraneous. All right. -1 works, though. It's definitely bigger than -2. Let's solve another one. Let's see here. I've got natural log of x plus natural log of x minus 4 equals natural log of x plus 6. Ooh, this time I won't forget the domain, though. Let's do domain. So x has to be positive from that one. Let's see. X minus 4 has to be positive, so x has to be bigger than 4. And then x plus 6 has to be positive, so x has to be bigger than -6. So thinking of a number line, I got to be bigger than -6. I got to be bigger than 4 and bigger than 0. So they all overlap when x is bigger than 4. So my domain is that x has to be bigger than 4. That's it. Those are the only numbers allowed when I solve this. That could be in the solution set. Well, I've got two logs with the same base being added again, so why don't I combine those by multiplying the arguments. Clean that up, I get natural log of x squared minus 4. But look, now I can use that one-to-one property. This natural log equals this natural log. Well, the only way two natural logs are equal is if their arguments are equal. And then once again, I get a quadratic that has the same solution set as the original log equation. Is this gonna... We're going to be able to factor this one. Let's see. Factors of 10 that differ by 1. Maybe not. Might have to do the quadratic formula. Maybe not. Maybe not. Let's go back. When I distributed x, it should have been 4x. Let's try that. Not that we couldn't have done the quadratic formula, not like we're trying to avoid the quadratic formula, but typically, since our focus is solving log equations, I don't want to have the problem also then have a quadratic formula, which takes a little bit longer. So factoring would be nice. Let's see if this works. I did forget to distribute the x. I distributed that x incorrectly, but I've adjusted it now. Let's see. 3 and 2, will that work? Negative, negative, no, because that wouldn't give me positive 6. So we're probably going to have to go with, going to get negative 1 and 6. But the only valid x values for these functions are bigger than 4, so 6. Once again, we got an extraneous. So we've got a lot of extraneous solutions in these examples. That doesn't mean you're going to have an extraneous solution for every log equation, but it's typically the one thing that people kind of forget about. They forget to check the domain and they just kind of start solving. So that's why I'm making such a big deal out of it in these examples. So, you should be checking, you should be on the lookout for it, but don't expect it to happen or to have an extraneous solution or solutions on every single problem you do. All right, well, let's turn our attention to some exponential equations. So these would be equations whose variables in the exponent, so they're exponential. And just like, because remember, exponential equations or functions are one-to-one, just like logs were one-to-one, they're inverses of each other. They have a similar property called the one-to-one property. So if you have an exponential function equal to another exponential function where they have the same base, the only way that's true is if their exponents are equal. Again, same restrictions as always. The base has to be positive. The base cannot be 1. But the exponents can be anything. So we're not worried about that. So this is just simply saying, look, if I've got 5 to the x equals 5 to the 7th, well, then x has to be 7. There's no other possible value there. 5 to the 7th equals itself, 5 to the 7th. And again, that's guaranteed by the fact that the exponential function y equals 5 to the x is 1-to-1. For every input, there's exactly one output. For every output, there's exactly one input. So very similar to logs because they're both one-to-one functions. Why do we care? Turns out that that's quite helpful. So if I have 4 to the 2x plus 1 equals 16, let's think about domain. We've got the variable is the exponent on an exponential function of base 4. But remember, for exponential functions, the exponent can be anything. So 2x plus 1 can be any real number. It doesn't really matter. So x can be any real number because it's the exponent on an exponential function. And exponents can be positive, negative, fractions, non-fractions, irrational, rational, doesn't matter. We're good. Any real number. So any answer we get is going to be an answer, unless we make a mistake, obviously, in our logic. But let's see what happens. So if I take 4 to the 2x plus 1, well, that equals 16. Well, one of the things I notice is that 16 is 4 squared. See, these are both the left and right side are the same exponential function. Well, our one-to-one property says that since this is true, then those exponents must be equal. So then that means x equals, well, let's see, that'd be 1 to a half. X has to be a half. 2 times a half is 1. 1 plus 1 is 2. 4 squared is 16. That's a true statement. Now, you might be thinking, whoa, 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 wait a minute. That's not how I would have solved it. That's not how I would have solved it, Mr. Franklin. I would have said, maybe some of you were looking at this saying, wait, that's exponential form, so why don't I switch it to a log? Log base 4 of 16 is 2x plus 1. Log base 4 of 16 is 2, and I get the same answer. And that's absolutely fine. So yes, there are options. Feel free to switch it to log form. For this next one, again, my domain, well, if you look closely, the variable is the exponent on base e, which means my domains are real numbers. I can have an exponent be anything I want. There's nothing preventing x from being any real number. So why don't I add this one over to this side? Now, why would I do that? Because then that clearly shows us that I have two exponential functions, both base e, equal to each other. So the one-to-one property says that their exponents must be equal. And then we get x equals 1. Get x equals 1. So again, no big deal. Use our one-to-one property. And all is well. Let's look at this next one. I've got a base 9, a base 27, and a base of 1/3. So one of the things domain, almost forgot. If we look at our domain, 2x and x squared, they're exponents. So again, x can be any real number. X can be any real number. All right. Well, here's what I noticed. Base 9, base 27, and base 1/3, those all can be rewritten to exponential functions that are base 3. So like, for example, 9 is the same thing as 3 squared. 27 is the same thing as 3 cubed. And 1/3 is the same thing as 3 to the negative 1. So I really have 3 to the 4x times 3 to the 3x squared equals 3 to the negative 1. Multiply those together and get 3, and then I add the exponents. Thank you, Algebra 1. And then I have a base 3 exponential function equals another base 3 exponential function. So the only way those could equal each other is if their exponents are equal. And once again, I end up with a quadratic that has the same solution set as the original. Will this one factor? Ooh, I think it will. So we get negative 1/3 and negative 1. And we know that unless I screwed up my logic somewhere earlier, those should both work because my domain is all real numbers. I don't have any extraneous solutions. We can check an answer real quick though. Let's check that negative 1. So that'd be 9 to the negative 2. So it'd be 1 over 81. And then times 27. So it'd be 1/3 equals 1/3. Yeah. So I think we're good. I'm not going to check the negative 1/3. Feel free to check it on your calculator if you want or need. Now let's try some more. A little bit more difficult this time though. Notice this time base 4, base 3, and base 14. Okay, those bases I cannot easily rewrite them to be the same base. Not easily. So maybe something else would let us tackle this a little quicker. First off, the domain, x is, once again, just in the exponent. So the domain is all real numbers. So how could I maybe approach this without rewriting them all to the same base? Well, what if I divide by 4? And then, again, trying to rewrite both sides to be base 3 or rewrite both sides to be base 7/2. I could do it. It could be done, I think. I don't know that it would make the problem easier, so I don't know if that's the way we want to go. Instead, notice that this is exponential form. And if I switch it to a log, it'd be log base 3 of 7/2 equals x, because logs equal exponents. And there we go, there's our answer. So it's done. We've solved for x. So x equals log base 3 of 7/2. Sometimes you'll see textbooks, they don't like the fraction. So they might write it like that. All textbooks and all, like basically whoever prepares answers, everyone's got their own little kind of quirks that they follow. Um, Me personally, I think I'd rather have just one single log as the answer. So I think I would just go with this. It's my personal preference. But what I'm going to ask you guys to do is anytime you get an answer that is a log, especially an irrational number, um, go ahead and get a decimal approximation for it because it's going to make checking your answers easier. So for example, this particular log is approximately, let's see, 1.1403. Not only that, it gives you a better idea of where the answer is on the number line. So 3 to what power is 7 halves? 3 to the first is 3, 3 squared is 9. So you know it's between 1 and 2, but I mean, a little bit more accuracy would be nice. So it's 1.1403. So let's go 4 decimal places. If your answer is not like a nice, neat, rational or integer. This next one, I've got base E. So again, could I rewrite both sides to be base 9 or base E? I could. I could. I don't know that I would want to. I think it's going to make it more difficult. But we could. So instead, though, I think it's going to be easier to say, hey, look, this is exponential form. Why don't we switch it to a log? So it's base E, so it'd be log base E of 9 is x plus 7. So that'd be natural log of 9 is x plus 7. So my answer is x equals natural log of 9 minus 7, which again is some irrational number. So I'm going to do a decimal. So natural log of 9 minus 7 is about negative 4.8028. And give both an exact answer and an approximate answer. So this is my exact answer. And then this is an approximate answer. I'm giving both. Having that approximate answer is going to make checking your answers a little bit easier. You'll see when you go to use the supplied answers, you'll see it's going to make it a lot easier when you've got that in there. By the way, twice now I've said that we could rewrite both sides to the same base, but it's not easy. Obviously, me saying easy or difficult is a relative term, but in my personal opinion, I think just switching it to log form is the way to go. But technically, we have properties from the last section that would let me write both sides to be the same base. So for example, I could leave the left side base E, but instead of having the right side be base 9, I could change it to base E. So 9 in base E is E to the log base E of 9. That's one of my properties from 5.5. And then they're both base E, so x plus 7 equals log base E of 9. So I get the same answer I got over here. So I mean, it's not longer. I just think the thought process is a little bit more cumbersome than just switching it to log form. That's my personal opinion, but it can be done. I definitely could rewrite both sides to be the same base if that's what I wanted to do. Which is what I've got here in the notes next. So another option is to use one of our properties. So here's our property that I just used up there. So just to hammer home the point that I could have rewritten both sides to be the same base. I've got those same examples that I just did. So divide by 4. And then instead of having 7 halves be the base, I could have the base be 3. But I got to use my property where if it's base 7, I got to use this property here. Or if this is a 3 and this is a 3 and this is 7 halves, then that equals 7 halves. So now I can set those equal and get x equals log base 3 of 7 halves, which is what I got before. And then I just worked it out up there, but Again, instead of base 9, I could leave it or change it to base e using that property. So x plus 7 then has to be log base e of 9, which will give me the same answer I got up there. So again, I find that more cumbersome. I think the thinking through that's a little bit more complicated than just switching it to log form. But again, that's personal opinion. Okay. Notice I've got those same two equations that we just solved. I've got them again because I'm going to show you a third way you could solve these. And then that way you have some choice about what makes the most sense to you when you go to do this. So same two equations, 4 times 3 to the x equals 14. I could divide by 4 again. And then I could use my one-to-one property from logs, which says that if two numbers are equal, then their logs are equal. So for example, 3 to the x is a number equals 7 halves. That's a number. So if these two numbers are equal, then their logs are equal. And you're thinking, which logs? Well, it turns out any log you want. You can pick any base you want. So for example, I could say their natural logs are equal. Their natural logs are equal. So if two numbers are equal, their natural logs are equal. Well, x is the variable on the argument, so I can bring that down front. And then divide, and I get x equals natural log of 7 halves over natural log of 3. And you're thinking, well, is that the same answer I got before? It is. If you run that through a calculator, you will get 1.1403, which is exactly what you had before. It turns out that's exactly the same. Now, how could you show it's exactly the same? Well, you could use your change of base formula. So these are both natural logs. So using your change of base formula, you'd go back to base 3. So it'd be log base 3 of 7 halves using the change of base formula. I'm not saying you have to do that. I'm just showing you, like, that's how you would argue that, hey, that really is the same thing as log base 3 of 7 halves, which is what we got before. I'm perfectly okay with you leaving it with natural logs. That's fine by me. The approximation is probably a little bit more useful in real world applications anyway. All right, now this right here, though, brings up an interesting idea that if two numbers are equal, their logs are equal. That's not exactly what the property said, but it is true. If two numbers are equal, their logs of the same base are equal because again, log functions and exponential functions are one-to-one. For every input, there's exactly one output. For every output, there's exactly one input. So matter of fact, back when we were writing those, so let's go back up here and revisit. We can actually go back and add to it. And if two numbers are equal, then their logs are equal, as long as those logs are the same base. So if two logs of the same base are equal, their arguments are equal. Or if two numbers are equal, two positive numbers are equal, then their logs are equal as long as those logs are the same base. And then for the exponential, again, exponentials are one-to-one, so we can go modify this one in a similar fashion. And if any two numbers are equal, then their exponential functions are equal. As long as those, again, the exponential functions have the same base and that base is positive, not equal to 1. Okay. So we could do Here's that other equation we've solved a couple different ways already. So again, if I wanted to, I could say, hey, look, these two numbers are equal. They're positive. E to this power is positive. 9 is positive. So if these are positive, then their logs are positive, as long as those logs are the same base. And you can pick any base you want. So you could pick natural log. I like picking natural logs because it's a little bit less to write. Then we could bring that exponent down front using our log properties. Natural log of e is 1. So we get x equals natural log of 9 minus 7, which is what we had before. Same thing we got before. Now, here's an equation we haven't solved yet. This is a brand new one. Notice both sides are completely different bases, and they both have variables in the exponent. So the domain is all real numbers because x is in the exponent. Again, we've seen lots of different ways to do this. I don't know that I think one's better than the other. It's whichever one makes the most sense to you. 5 to a power and 3 to a power, those are both positive numbers. So one way we could solve this is say, look, these two positive numbers are equal, therefore their logs are equal. Now, which log? I don't know. Again, I kind of just use natural logs. Just because it's a little bit less to write, ln instead of log. But that's my personal preference. And then I'm allowed to bring those exponents down using my properties from earlier. And then it just turns into an algebra 1 equation. And you're thinking, whoa, I didn't solve anything like this in algebra 1. You didn't. There wasn't nothing like a natural log of 5. But natural log of 5 is just a constant. It's just some real number. No big deal. So, I mean, as far as how we solve the rest of this equation, I'm just going to use properties from algebra 1. For example, I'm going to distribute the natural log of 5 and get x times natural log 5 minus 2 times natural log 5. I'm going to distribute the natural log of 3 and get x times 3 natural log 3 plus, I guess, I don't know why I wrote it that way, but I'm going to get 3x times natural log 3. Then I'm going to get 2 times natural log 3. Then I'm going to clean this up using properties. This is going to be x times natural log of 5, but I'm going to write this as natural log of 25 because 5 squared is 25. I'm going to bring this 3 up and write this as natural log of 27. I'll bring that 2 up and write that as natural log of 9. Well, I've got some like terms, right? These both have an x, so I'm going to bring those to the same side. Then I'm going to add the natural log of 25 to the other side. Now I'm going to use notice they both have an x, so that's the greatest common factor. And we're almost done. I have two logs with the same base being subtracted, so this is x times natural log of 27 fifths. These two logs have the same base and are being added, so this is natural log of 9 times 25. That'd be what, 225? You think? And then divide. So I get x equals, that's a perfectly acceptable answer for me. Another way that you could use the change of base formula, this would be log base 27 fifths of 225. I mean, that's okay too, I guess. I don't have a preference. It does appear to be an irrational number though, so I would go ahead and get a decimal, so checking your answer is a lot easier. And it looks like x is just a little bit bigger than 3. So again, the idea here was just showing you how we can use all these properties that we've discussed in our definitions of exponential and log functions and use those, exploit those to solve log equations and exponential equations. So you have lots of options available to you when solving such equations.